You ever wonder how your phone just knows what you want to buy next? Or, how scientists can predict disease outbreaks before they even happen? Well, the answer is this incredibly powerful process called data mining. And today, we're going to crack its code together.
I mean, think about it. Every single click you make, every transaction, every sensor reading out there, it all adds to this massive digital ocean that's growing from terabytes to petabytes. It's an absolutely incredible resource. But let's be honest, all that raw information is basically just noise without the right tools to make sense of it all.
So that's the big question, isn't it? How do we pan for gold in this digital river? How do we possibly find the meaningful, the predictive, and often totally invisible patterns that are hidden deep inside all that data? Well, that is the entire quest of data mining. To guide us on this quest, here's our roadmap. We'll kick things off with what makes a good model in the first place, then dive into a fundamental choice between two types of data. We'll look at learning with a teacher versus kind of finding your own way, compare different modeling philosophies, and then wrap up with the single most important takeaway.
First up, the quest for patterns. Look, before we even start digging, we need to know what we're looking for. I mean, what separates a truly useful model from a completely useless one?
So any good data mining model, it really has to check three big boxes. First, accuracy. It's got to be right. Simple as that. Second, interpretability. We as humans need to understand how it's making its decisions. A black box isn't always helpful. And finally, efficiency. It has to be built fast, even with gigantic data sets. Otherwise, it's just not practical. All right, now let's get to what is maybe the most crucial decision in any data mining project. This one choice basically dictates the entire path you're going to take and all the tools you'll use. I like to call it the tale of two data sets. And this slide right here frames that central choice. It all boils down to your data. Do you have an answer key? If your data is labeled, meaning you already know the correct answers for your training examples, then you're on the supervised learning path. But if your data is unlabeled, and your whole goal is to just discover hidden structures on its own, then you're on the unsupervised path. This diagram shows that exact moment of choice. See? After you get your data ready, you hit this fork in the road. The path to the left is for supervised tasks, things like prediction. The path to the right is for unsupervised tasks, like finding hidden groups or associations. This one single decision shapes your entire project from here on out. So, let's explore that first path, supervised learning. The best way to think about this is like learning with a very, very patient teacher who already knows all the answers. The absolute key here is that your training data comes with labels. You're showing the model examples of, say, a fraudulent transaction, or you're showing it what a spam email looks like. The model's job is to learn the rules from all these examples so it can accurately predict the right label for new data it's never seen before. Now, on this path, you have a whole toolkit of really powerful techniques. For example, decision trees create these simple flowchart-like rules to classify data, while something way more complex, like artificial neural networks, which are inspired by the human brain, can learn incredibly subtle patterns. Each tool is perfect for a different kind of prediction problem. Let's make this concrete. Take a look at this artificial neural network. If you wanted to teach it to recognize different voices, you would feed it thousands and thousands of audio clips, and each one would be labeled with the correct speaker's name. The network then adjusts all its little internal connections over and over until it can accurately tell you who is speaking. That, right there, is supervised learning in action. Okay, let's rewind. Let's go back to that fork in the road and take the other path, unsupervised learning. This time, it's like being an explorer in a new land. You've got no map, no guide. Your job is to find the structure, all by yourself. The key phrase here, and you really have to remember this, is no pre-existing labels. The data is just raw. You're not trying to predict a known answer. You're trying to discover the answers. You're asking the algorithm, hey, can you find any natural groupings or hidden structures in here for me? By far, the most common unsupervised task is something called clustering, just finding natural groups in your data without any labels to guide you. Think about sorting customers into different market segments. A classic algorithm for this is k-means, and its logic is surprisingly simple. Let's see how it works. The whole process is really elegant. You start by just randomly dropping a few centers into your data. Then, the algorithm just repeats 2 simple steps over and over. First, it assigns each data point to whichever center is closest, and second, it updates each center by moving it to the middle of its new group. It just keeps doing this little assign and update dance until the groups settle down and stop changing.
So it all starts with what is basically a random guess. As you can see in the diagram, the initial centers are just placed arbitrarily. This leads to a really rough first attempt at forming clusters. It's not perfect by any means, but it is the crucial first step.
And then the magic happens. With each cycle of assigning and updating, those centers start moving towards the true hearts of the clusters. You can see how they shift and refine their positions until the groups become stable. And just like that, the algorithm has found the natural structure hidden in the data. And remember, it did all of this without any pre-existing labels. Okay, so we've chosen our path, supervised or unsupervised. But wait, there's actually another layer of choice here that reflects a whole different philosophy. Do we force a structure onto the data, or do we let the data create its own structure? I like to think of this as the cookie cutter versus sculpting clay approach. Parametric models are the cookie cutters. They assume the data will fit a specific shape, like a straight line. They're super fast and efficient. But if your data is actually shaped like a star, your circle cookie cutter is not going to work well. Non-parametric models, on the other hand, are like a lump of clay. They're flexible and they let the data itself determine the final shape, no matter how weird or complex it is. And here you can see the key trade-offs, crystal clear. Parametric models are fast and efficient, but only if your data actually fits their strict assumptions. Non-parametric models are way more flexible and can handle complex data, but they often need a lot more data and a lot more computing power. The right choice really depends on how complex your problem is and what your data actually looks like.
Which brings us to our final and, I think, the most important lesson in this whole process. What should you really take away from all of this?
It's this simple but really profound idea. There is no single best algorithm. There just isn't. A model that's an absolute genius for one problem might be completely useless for another. Context is everything. The nature of your data and the specific question you're trying to answer will always determine the right tool for the job. So ultimately, data mining isn't about memorizing a long list of algorithms. It's about understanding these fundamental choices, supervised or unsupervised, parametric or non-parametric, so that you can pick the right approach for your unique challenge. So the real question is, what hidden patterns are out there just waiting for you to find them?